Hi everyone, this is the key to the Unit 4 practice exam for Physics 251. Number 1, a 3.00 meter rod is found to have expanded 0.091 centimeters in length after a temperature increase of 60 degrees Celsius. Calculate the rod's coefficient of linear expansion. Okay, so we've got the initial length of the rod, and we have the delta L in a different unit. So you'll have to convert one of those to the other unit. It doesn't necessarily matter which one you choose, but I decided to do both of them here as an example. So we've got a delta T of 60 degrees Celsius. That is also something you can treat as 60 Kelvin. That works because Kelvin degrees and Celsius degrees are the same size. So we're solving for alpha. That's going to be delta L divided by the initial length in the appropriate unit and the temperature change. And regardless of how you do it, you'll end up with the same numerical value, whether you use centimeters and centimeters or meters and meters. I didn't do it an additional time for either of those distance units and Kelvin, because again, you would just end up with exactly the same value. So alpha here would be 5.1 times 10 to the negative 6, either inverse Celsius degrees or inverse Kelvin. On to problem 2. It reads, a 550-gram block of 93 degrees Celsius lead is placed in an insulated cup containing 150 grams of 24 degrees Celsius water. Calculate the mixture's equilibrium temperature. The specific heat of lead is 128 joules per kilogram Kelvin. Okay, so we've got the masses of our two materials. We have the initial temperatures of our two materials and the specific heats. We've got water-specific heat, and I've got the temperatures given in both Celsius and Kelvin degrees. I'm going to want Kelvin because of the fact that I have a specific heat that is dependent on Kelvin and not dependent on Celsius. The total amount of heat lost by the metal is going to be the same as the amount of heat that's gained by the water. And because the metal is going to start at a high temperature and end at a lower one, I know that its delta T is going to be negative. So in order to counteract that, I'm going to put a negative on that same side. It also reflects the fact that Q is flowing out of the metal and into the water. I can fill in what I know, but I have the same unknown T final showing up on both sides of this equation. Solving for T final gives me a temperature that falls in between the initial temperatures of the lead and the water. If you think about that, it makes sense because those two systems are going to meet somewhere at some equilibrium temperature. So it wouldn't make sense if the water ended up colder than its initial temperature or if the lead ended up hotter than its initial temperature. In Kelvin, this works out to 303.950. To convert that into Celsius, that is something that would round to 31 degrees Celsius when sig figs are applied. Question 3. If the mixture in question 2 took 200 seconds to reach an equilibrium temperature, what is the cooling constant? The cooling constant is a value that we encountered in the latent heat of the linear expansion lab, the second to last one that we did this semester. And we were given an expression that would let us calculate the temperature of some system so long as we knew the ambient temperature, its temperature at a time of 0 seconds, and then a cooling constant and the amount of time that spends actually cooling down. So here we know the delta T is 200 seconds. We know the lead's temperature is going to be T0 because we're not really concerned with how the water is warming up, instead how the lead is cooling down. The ambient temperature is going to be 297 Kelvin, and we've got our final temperature from our previous question. I know everything in this statement except for the cooling constant K. So I can just set this up. I can Initially subtract off 24 degrees Celsius from each side, leaving me with 6.956 degrees Celsius. And then 93 minus 24 gives you 69 degrees Celsius. At this step, you can just take a natural log of both sides, and taking the natural log of the right side will leave you with just the e to the minus k times 200 seconds. I didn't note this beforehand, but the assumption is that you've already divided both sides of this equation by 69 degrees Celsius. So you're left with the natural log of that ratio on the left, and then just the negative k times the time interval, 200 seconds. Because we're calculating the natural log of a quantity that's less than 1, that's going to yield a negative sign. That's going to be canceled out by this negative sign. So you'll end up with a k that has a positive value, and it ends up with units that are just 1/2. So k is 0.011 inverse seconds. Number 4, Lake Erie contains about 4.8 times 10 to the 14 kilograms of water. If the lake has an average temperature of 45 degrees Fahrenheit, how much thermal energy would it need to lose in order to freeze over completely? We have the mass of the water. We have the initial temperature of the water, initially given to us in a unit that's not going to work out. So we can go from Fahrenheit to Celsius and then into Kelvin. We know that water freezes at 0 degrees Celsius, so that's going to be equivalent to 273 Kelvin. And we have the specific heat for water and the latent heat of fusion for water, because we're concerned with doing two things in this process. One, there's going to be a certain amount of heat loss that's going to be required in order for the water to get to the freezing point. And then an additional amount of heat loss that is required in order to actually change the phase. So I have Q total as the sum of these two magnitudes. The Q just needed to chill the liquid to 273 Kelvin, added to the Q required to freeze that liquid. If we look at the first term first, Q to chill the liquid to 273 Kelvin is going to be an MC delta T calculation, because there actually is a temperature change happening here, but no phase change. I have the mass, the specific heat, and the delta T for the water. And that ends up working out to a loss of 1.48 times 10 to the 1.4823 times 10 to the 19 joules of energy. Next, we can move on to the heat that has to be lost in order for the liquid to freeze. That's just going to be the mass of the water times latent heat of fusion for that water. So I apologize for the pagination and getting a little awkward here, but this is 4.8 times 10 to the 14 kilograms times 3.33 times 10 to the positive 5 joules per kilogram. Remember, latent heats do not have the temperature unit in the denominator because that process is associated with a phase change, but not a temperature change. So multiplying mass times energy per mass is just going to leave you with an energy. And I'm treating this as a negative because I know this is the heat that the water has to lose in order to change its phase. That's negative 1.5984 times 10 to the 20 joules. And if I take the absolute values and then add them together, I get the total heat that has to be lost in order to achieve that two-part process. This is 1.7466 times 10 to the 20 joules, which we can round to 1.7 times 10 to the 20 joules when we apply sig figs. Number 5, refer to the set of thermodynamic systems shown below. Use the first law of thermodynamics to determine the amount of energy exchanged in each example. When appropriate, draw an arrow to indicate the direction of energy exchange. Okay, this is a screen cap of our practice test with the rectangle representing the thermal energy change of the system, and then arrows on the top and bottom of that system that can either indicate heat being transferred into the system or out of it, or work being done on the system versus by the system. The first law of thermodynamics just states that the change in thermal energy is going to be equal to Q plus W. So for case A, I know that I have a positive thermal energy change, but there's a negative heat here. So heat is being lost by the system, all the while the thermal energy is increasing. The only way that we can achieve this is if there's work that's being done on the system. So I could communicate that with an arrow that is heading into the rectangle. And if I were to solve this for the magnet or the value of W, I'd get positive 250 joules. So you put in 250 joules of work, but the only energy that's retained is 150 joules. That means that 100 joules of energy flow out of the system as heat. For B, we have the work done on the system, and we know it's on because the arrow is pointing into that rectangle. And we've got heat being added to the system, and we know it's added for exactly the same reason. So if 350 joules of energy combined with 200 joules of energy, that will tell us what the thermal energy is. And let me scroll down a little bit further here. So because the thermal energy change is a positive, we can treat that as an overall thermal energy gain. If we go back and take a look at this statement for part A of this problem, we know to characterize this work as being done on the system simply because it's a positive. And then back up here to the top, if we look at case C, I know that the system is losing 25 joules of energy, but it's also doing 120 joules of work on the environment. That's the same as saying that the work is being done by the system instead of on the system. So if there are 120 joules exiting, and I know that overall there's a loss of 25 joules, I can just come back down to the first law of thermodynamics here to solve for Q, and I get Q that's a positive. So I would have to add 95 joules of heat in order to allow the thermal energy of the system to decrease by 25 joules and to simultaneously allow the system to do 120 joules of work on the environment. So this heat is being gained or added because I've found a Q that has a positive value. Number 6, 2.15 mole of monatomic gas A initially has 5,670 joules of thermal energy. It interacts with 1.85 moles of monatomic gas B, which initially has 9,180 joules of thermal energy. Calculate the initial temperatures of each gas and calculate the final thermal energies of each gas. Okay, so we can start with gas A, and we're solving for using the thermal energy to solve for a temperature. So to cut down on the subscripts, I just have E initial A, where this E refers to thermal energy and not mechanical or any other form. That's got to be equal to the number of moles of gas that exist in system A times the molar specific heat for a constant volume process. And we know that for monatomic gases, that's just 3/2 times the universal gas constant, capital R. And then I can multiply that by T initial for gas A, not delta T for gas A. I just want to figure out the temperature before these two systems interact with each other. Rearranging this to solve for T initial for gas A leaves me with 212 Kelvin when sig figs are applied. And I use exactly the same expression for gas B, so I didn't write it out in additional time. I just used the same expression, but with B as a subscript, so I can swap in the new energy, the new amount of gas, but 3/2 times 8.31 joules per mole Kelvin is going to show up in both of these denominators. And I end up with 398 Kelvin. On to part B. Now we're assuming that these systems are allowed to interact with one another, and we know that the equilibrium temperature that the systems both reach will have to be somewhere in between the two initial temperatures that we calculated. So somewhere between 212 Kelvin and 398 Kelvin. However, this question is asking us for the final thermal energies. We could take this one step further and determine what the final temperatures of each system would be, but we would just get the same number twice. In order to figure out how much energy is in system A after they've interacted with one another, I can just take the ratio of the material in the system that I can attribute to system A. So Na over the total number of moles times the total thermal energy, and I get 7,980 joules. So that immediately tells me that gas A had to pick up some energy from gas B. And that might seem obvious if you take a look at the temperatures. We saw that system B started off with the higher temperature, so it's going to be the one that loses heat to system A, where they meet somewhere in the middle, but this just confirms that. And we can now do the same thing for system B. NB divided by the total amount of gas times the total energy leaves us with 6,870 joules. So we know that gas B has lost thermal energy because it began with 9,180 joules. Number 7, 0.75 mole of helium gas undergoes the ideal gas process illustrated in the PV diagram below. Complete the table, so we need to find a handful of quantities for state 1 and state 2. I'm not told anything at all about state 3. So this is something that we can start with the ideal gas law. And if we start with state 1, we can recognize that this isotherm between state 1 and state 2 represents a line of constant temperature. So I know both T1 and T2 at this point, and they are 300 Kelvin. I converted it to Celsius here, not because it was necessary, but because we're trying to fill out a table that has the temperatures in 2 different units. So that automatically gives me the answer to T1 and T2 in Celsius. It would just be 27 degrees Celsius. I don't know the volume at state 1, but I do know the volume at state 2. And I know the pressure at state 1, but not the pressure at states 2 and 3. I can figure out the volume at state 1 just by using the ideal gas law. So solve this for V1, that leaves you with N times R times T1 over the pressure at state 1. And we're given pressures in atmospheres on this y-axis, but in order for the units to cancel appropriately, we'd have to convert that from atmospheres into pascals. And I just used the conversion factor here. So 1 atmosphere is equal to 1.013 times 10 to the 5 pascals. That means that the pressure at state 1 is 1.013 times 10 to the 5 pascals. So when I plug that in, I get 0.01846, and the units are cubic meters. We can see how that works out if we remember that a joule is a Newton times a meter. So dividing that by a Newton per square meter is going to wipe out both of the Newtons and just combine the meter squared with the meter that was native to the joule. So we've got this volume in cubic meters. Now, in order to represent that in liters, I can use this conversion factor. So this is one that's on our formula sheet, even though I don't believe I used it in class at all, but it is 10 to the 3 liters is equal to 1 cubic meter. So all I have to do is take 0.0185 cubic meters, multiply it by 1,000, and I've got the number of liters. That's 18.5 liters. And that volume is also going to apply to state 3, even though I don't know anything else about state 3 just yet. However, state 3 and state 1 share a volume. We know everything there is to know about state 1. We can move on to state 2. And I know everything except the pressure in this scenario because the isotherm tells me that T2 is also 300 Kelvin, and we were told that the initial volume in cubic meters is 0.150. Solving the ideal gas law for P2 now will give us a pressure that's in pascals, and it is 12,465 pascals. So that's less than 1.013 times 10 to the 5 pascals. And we could have guessed that by looking at the scale that's on the y-axis. We knew we were going to get a smaller value for P2 and P3. And here we have gotten a smaller value. And now, in order to figure out how to express that pressure in atmospheres, I can use the same conversion factor, but just in the opposite direction. So taking 12,456 pascals and dividing it by 1.013 times 10 to the 5 pascals gets me back into atmospheres. And again, I get something that is smaller than 1 atmosphere. It's about 0.123 atmospheres. So I now know everything there is to know about state 2. I can move on to state 3. The pressure at state 3 is going to be the same as the pressure at state 2 because my process from state 2 to state 3 is an isobaric compression. So the pressure stays constant while the volume drops and the temperature drops. To figure out the temperature that correlates with state 3, I can just go back to the ideal gas law. So I've got the pressure at state 3. I have it in pascals or newtons per square meter because I know I'm going to need to combine it with a volume in cubic meters. Divide that by 0.750 mole multiplied by 8.31 joules per mole Kelvin. And I end up with 37.0 Kelvin. So coming back up here, I knew that I should have gotten a temperature for state 3 that was less than 300 Kelvin, simply because isotherms that are closer to the origin represent lower temperatures. So it makes sense that I did get a temperature that is less than 300 Kelvin. The last thing that we would need to fill out in our table is the temperature at state 3 in Celsius. So here is where I did mess up. This should be degrees Celsius instead of K for Kelvin. But now I've got everything filled in. The volumes in 2 different units, the temperatures in 2 different units, and then the pressures in 2 different units. And I also applied sig figs here so that all of this is represented to 3 sig figs. Now, all of that was part A of number 7. Part B now investigates the work done by the process. So this is exactly the same PV diagram, but now I am trying to account for the area below the curve for each of these 3 sections, from state 1 to state 2, 2 to 3, and then 3 back to 1. Now, there are different expressions that we can use for each one of those steps of the process. And because going from state 1 to state 2 is an isothermal expansion, I'm going to use this version of the work expression. So the temperature remaining constant means that work is going to be equal to minus nRT times the natural log of V2 over V1. You can think of this as V final over V initial if you like. I know all those quantities because I know everything that there is to know about the state of the gas at state 1, 2, and 3. I'm trying to figure out how to explain what happens in between those states. So when I plug in the volumes here and take that ratio, as long as the units cancel out, will be good here. So I'm in cubic meters both times. I'm going to be taking the natural log of a value that is, this ratio is going to be bigger than 1. So I'm going to get a natural log that is a positive value. But minus nRT has to give me a negative. So I end up with negative work. And if you think about what would have to happen in order for this gas to expand, imagine the gas pushing against a piston so that it can make the entire volume of the system get larger over time. that will cost the system energy as opposed to adding to the system's energy. So we can interpret that as work done by the gas or by the system on the surroundings, as opposed to work done by the on the gas by the environment, or maybe by you actually pressing down on the piston. So this is telling us the area below the entire isotherm, even though we know that we don't just go from state 1 to state 2 and stop. Instead, there's going to be an isobaric compression that follows that. So the net work is just going to be what is like the net area below these two curves. That means I can subtract out this blue area. The work from state 2 to state 3 is going to be minus P times delta V, where the pressure is a constant. I know that value is 12,465 newtons per square meter. Delta V is going to be a negative value because I'm going from a big volume to a smaller one. That's going to cancel out the negative that is already present at the beginning of this work equation. So I've got 1,640 joules, and it's positive because that work would need to be done on the system in order to make the gas compress, as opposed to the expansion that we saw from state 1 to state 2. Then finally, if we look at the process from state 1 to state 3, there is no equation that matches up with this because there is no area below that vertical line. So the work there has to be 0. That means the net work is just going to be the 3 of these added together. And I have the unrounded values here for the work from state 1 to 2 and then 2 to 3. Add that to a 0, I get negative 2,277.76 joules, which I can express as negative 2,280 joules when I apply 3 sig figs. Number 8, a cube measuring 18 centimeters on each side contains 3.90 grams of helium at 20 degrees Celsius. 1,500 joules of heat energy is transferred to the gas. We want to find the RMS speed of the particles in the gas before anything has happened, so before the heat energy has been transferred in. And then we want to find the final pressure if it's constant volume, and then the final volume if it's constant pressure. And those are two unique situations. We know that the constant volume process is one that would cost no work, but instead would require that you either transfer heat into the system or out of the system. And then for the constant pressure system, you have to have a combination of work and heat. So let's look at what we know about this, this cube that contains gas. We have the volume in, this should be cubic meters, but this is a 2 subscript instead of a 3. I apologize for not catching that before. The mass of the gas in kilograms is 3.90 times 10 to the negative 3 kilograms. And we know that it starts at 20 degrees Celsius. That's 293 Kelvin. Eventually, 1,500 joules of heat is transferred into the gas. But first, we just want to figure out what the RMS speed is. And because of the fact that we know that this is helium, and we know that a helium nucleus has got an atomic mass of 4, I can take 4 times the atomic mass unit, and that's going to be the mass of each one of these particles, where I'm thinking of each helium atom as its own particle. So I lost the radical right here in this last step, but it shows up again on the line below. But I have 3 times Kb times the initial temperature, all that divided by 4U. And when you end up taking what turns out to be a pretty small energy divided by an even smaller mass, that's going to leave you with a fairly large positive value to take a square root of. And that is 1,351.61 meters per second, which I can take to 1,350 when I apply sig figs. Now, to figure out the final pressure of the gas, if it's a constant volume process and the final volume if it's constant pressure process, I need to know how many moles of gas exist in the system. So N is going to be equal to the mass of the gas divided by the molar mass. And again, because this is helium, that molar mass is going to be 4.0 grams per mole. This is not the type of thing that I would require you to have memorized. If it's going to be relevant on an exam question, that would be given to you unless it was the thing that you were solving for. So 3.90 divided by 4 gives me 0.975 mole. So I don't know the pressure of the gas at T is equal to 0, but I could use the ideal gas law to figure out what that is. So that gives us 407,057.48 pascals, because a joule per cubic meter is exactly the same as a Newton over a meter squared. So that's the initial pressure. I'm trying to find a final pressure, but I know that the volume of this system is not being allowed to change for part B of number 8. So this is an isochoric heating because you are transferring heat into the gas, isochoric because of the constraint that the volume can't change. I can solve this for delta T, and I get 123.08 Kelvin. So that's a temperature change, not the final temperature, but that means that I can use it to figure out what the final temperature is. So if delta T is T final minus T initial should be T initial plus delta T. The final temperature is 416.08 Kelvin. And to find the temperature at the, not the temperature, but the pressure at the final state, I can start over with the ideal gas law, or I can go to one of those 3 named laws that we encountered in the macroscopic description of matter chapter. We encountered Charles's law, Boyle's law, and then Gay-Lussac's law. And that's the one that pertains to scenarios where the volume of your system doesn't change. So P1 over T1, or P initial over T initial, is going to be P final over T final. So I can solve this for the final pressure. And I find that it is 5.8 times 10 to the 5 pascals. So approximately 578,000 pascals compared to 407,000 pascals. So it's not too hard to visualize or too hard to guess that transferring heat to that gas but not letting the gas change its volume in any way would have to result in a pressure increase. Now for that second state, or that second expansion, what's the final volume of the gas if the process takes place at a constant pressure? We can still carry over the pressure that we calculated for the isochoric heating portion. Only now we can change our energy statement. This heat is going to be equal to the number of moles times the molar specific heat for constant pressure times delta T. And again, we have a delta T that is going to be a positive because we're adding heat to the gas. It's not necessarily immediately obvious what the sign of the work would be, but if you think about what this process would look like on a PV diagram, there's a pretty big hint. But at this point, we can just figure out what the temperature change is. You get about 74 Kelvin. And just like before, if we know the initial temperature and we have a delta T, we can solve for the final temperature, which is 366.96 Kelvin. And now, because I have a constant pressure process, instead of Gay-Lussac's law or Boyle's law, we can use Charles's law. V initial over T initial is equal to V final over T final. So I can solve this for the final volume. You get 0.007304 or 7. Yeah, I think it's 7304. There should be cubic meters. I just snuck it right below. If I apply sig figs, I can put that into scientific notation and express that as 7.3 times 10 to the negative 3 cubic meters. Number 9. A heat engine does 12 joules of work and exhausts 18 joules of waste heat during each cycle. Its cold reservoir has a temperature of 20 degrees Celsius. What is its thermal efficiency, and what is the minimum temperature of its hot reservoir? So the first time we encountered the terms hot reservoir and cold reservoir, it was when we were talking about conduction, which is heat exchange by systems that are either in indirect contact or direct contact. Here's how we can represent that heat engine with a heat engine diagram. I've got the hot reservoir up here at the top. I have the cold reservoir at the bottom, and I don't know what the minimum temperature of the hot reservoir is yet. But the fact that I know that I get 12 joules of output work in exchange for exhausting 18 joules of heat as waste, and that the cold reservoir has a known temperature of 293 Kelvin, I can use this expression for the output work. This is going to be equal to QH, so this is the heat that it would cost you, in a sense, minus QC, which is the exhaust. The difference between those is the difference between the output work and the exhaust heat is going to be 12 joules minus negative 18 joules, so 12 plus 18, in other words, you get 30 joules of energy. So you put in 30 joules of energy. This process is going to create 18 joules of exhaust, but the leftover work is now being output so that you can harness that for maybe an additional job. That was our first step so that we could find thermal efficiency. And the expression for that is eta is equal to the output work divided by QH, which is something that we can also hear described as the efficiency being what you get versus what you had to pay, because the QH is the heat that you had to transfer into the system in exchange for getting 12 joules of output work. That ratio, 12 over 30, is 0.40, so this is a 40% efficiency heat engine. And finally, number 10, 600 milliliters of 20 degrees Celsius water is placed in a freezer with a coefficient of performance equal to 5.00. How much heat is exhausted into the room as the water changes to -1 degree Celsius ice? All right, so we'll start by finding the mass of the water, which we can do by taking the density of water, that's 1,000 kilograms per cubic meter, and we can combine that with the volume that we were given. It was given in milliliters, but we can convert that into cubic meters. We just divide through by 1,000, and we end up with, not dividing through by 1,000, but 10 to the 6. And we end up with 6.00 times 10 to the -4 cubic meters. We have the initial temperature of the water. We know that the phase change is going to happen at 0 degrees Celsius, but that's not the end of this process. After the water changes phase and becomes ice, it also is further chilled down to -1 degree Celsius. So this is what our diagram would look like for this refrigerator. We provide input work, and we're able to end up with QH, so the heat that's sort of being dumped into the environment, so like the exhaust heat, and then QC would be what you get in this scenario. The mass of the water is going to be 600 grams, which is 0.600 kilograms. And now the energy loss, or the heat loss really, is going to be the magnitude that it has to be lost in order for the water to chill, added to what has to be lost in order for it to freeze, added to what has to be lost in order for the ice to chill. So we can just break this down into 3 steps, where both of the chilling steps are going to be MC delta T calculations. The mass is known. We're talking about liquid water initially, so the specific heat would be 4.19 4,190 joules per mole Kelvin. And we need to get from 20 degrees Celsius down to 0 in order for the water to be capable of freezing. That is exactly the same as a negative 20 Kelvin temperature drop. So that yields 50,280 joules of heat that has to be lost. Next, to freeze the water, we can use the latent heat of fusion for water, multiply that by the mass, and I get 199,800 joules. I put a negative here because this is another heat loss. The water has to lose this heat in order to complete its phase change. And then finally, I have another MC delta T term, only this time the C, the specific heat that's relevant, is the specific heat for ice, which is different than the specific heat for liquid water. I'm only trying to get this ice to go from 0 degrees Celsius to negative 1 degree Celsius. So in Kelvin, that's just a loss of 1 degree. And I end up with a negative heat here, negative 1,254 joules. Finally, I can just add all of these magnitudes together to figure out the total heat loss. And because this is a refrigerator, this represents QC, 251,334 joules. Now, we're looking for the coefficient of performance, which is capital K for a refrigerator. And just like before, it's the ratio of what you get and what you have to provide or what you pay for, where QC is the the heat that is being taken out of the water while this process is playing out. It's going to be the same as the magnitude of Q total we calculated further up. And then the cost is now input work that you would have to provide, or realistically that the air compressor would have to provide. So solving this for the input work gives us the heat that the water has to lose divided by the coefficient of performance, and that gives us 50,266.8 joules, which we can express as 5.0 times 10 to the 4 joules. And just one last comment here. Because this is a refrigerator, the exhaust is not QC, instead it is QH. So QH can be calculated from this energy statement. QH is QC plus the input work. I know both of those quantities, and I can add those together. We get 301,600.8 joules, which is 3.0 times 10 to the 5 joules when sig figs are applied.